Today, we're going to talk about gravitational lensing. And gravitational lensing is based on Einstein's theory of general relativity. General relativity. And general relativity is really our theory, our current theory of gravity. Okay, so general relativity you can really think of as gravity. Used to be Newtonian gravity, and now we think of it as general relativity. And the difference between general relativity and Newtonian gravity is that what Einstein said was that gravity is really due to the curvature of space-time. So this is really the curvature of space-time. The idea being that there's no force of gravity in the same sense that we used to think about it, but that how space and time are curved is what dictates how things move around massive bodies. Okay? And there's a famous equation called the Einstein field equation. Einstein field equation, which basically says that the curvature of space-time is somehow equivalent to the matter content. Matter content of space-time. Okay? And what I really mean by that is, so if we start with space-time without any matter in it, it looks flat. There's no curvature whatsoever. And let me draw you a picture of that, but I'll have to erase all this stuff first here. So, picture of curved space or flat space-time. Really, I can just think about it as a grid. This is just one way of thinking about it here. And so, if I just draw a bunch of straight lines like this, and then cross them at right angles, the idea being that this is nice and flat. There's really no curvature. All the curvature here is just because of my unsteady hand, right? So that's what flat space-time looks like. Now, if I wanted to put the Earth sort of in the middle of this, green and blue, okay, a lot more blue than green, then it would look something like this. Okay, so this is a picture of curved space-time. And the idea here being that a path that if I was going to go along in this curved space-time, so the matter in the center, the Earth, is making the space-time curve, and then the matter, if I had other matter here, so it would not travel in a straight line, but it would actually curve around. Okay, and that's the idea of gravity, right? So if I think about this in a Newtonian sense, the Earth is sort of pulling this thing into a curve. But you can just think about it, because of space-time now, as something going into a banked curve. It's not the Earth's gravitational field pulling it, but rather the fact that the Earth has bent space-time, and I'm moving along in this curved field. And if I'm closer, I'm going to move in a even more of a curved line like this. Okay. And what's amazing is that this is true not only of particles, of other massive particles, but of light. Now, light doesn't usually have mass. It's massless. But because it's just the path that is moving along in space-time, it is still affected by this bending. And so we get the bending of light. Okay? And the idea here is that, so if I look at this picture, this is from a textbook, Addison Wesley textbook, then if I look at where star A is, for instance, so star A will make a bright red star over here, okay? And because it is affected by this curvature, the light from it gets curved as it moves around. Here's pictured as the sun as it comes towards Earth. Now, if there was something very far away, another star, star B, let's make that one green over here, okay, then it doesn't get curved as much because it's further away from the sun. Okay, it doesn't go through as big a banked turn, right? So those two stars to us look like they're right next to each other, right? This dotted line over here, this red dotted, this yellow dotted line, but now I'm dotting it with red again. That's where it looks like star A is, because all we see is the sun the light from this faraway star coming, we think it's coming straight at us. If we assume it's coming straight at us, we think that the star is here. That's its apparent position, right? The apparent position of star A. But it's actually over here. Its true position's there. And then B is basically where we think it is. It's bending just a little bit, but not as much, okay? So that's the idea of how light bends around things. Now, you can imagine that if something is behind the sun directly, so say something was directly behind the sun over here, okay, so there's another star, maybe a big galaxy, then light from it, let me erase some of my extra stuff here. Light from it could get bent both ways around the sun, okay, come like this, or like this. And this is exactly what happens in a lens, right? If I had a normal light lens of some sort, like a magnifying glass, right? All of the light that's coming straight in to the lens gets focused down to a point, right? And that's where we would have our poor little ant buddy, right? This little antenna, and that's little boys burn, right? Well, I definitely used to try and burn all kinds of things with my magnifying glass. And so this is that's what a lens does, right? Is it either, in this case, it focuses the light somewhere else. So that's what's happening here, is that all the light from this distant star, or it could just as well be some big galaxy back there, as it moves, it gets bent by all this stuff. And so we end up seeing something that we call Einstein rings, which of course are named after Einstein because he sort of predicted them, which are, if we look at, if you're looking at the sun, say in the middle, you'd see these weird rings of light coming around the star like this. Okay? So to recap, Einstein's theory of general relativity tells us that the matter in space-time tells space-time how to curve. So that's what the sun is doing here, right? The sun is telling space-time how to curve around it. And then that curvature is telling other things, other matter, and in this case light, how to move through that space-time. And in this case, when we have some central body, something between us and some far distant thing, like this galaxy or star, then the light can actually get bent all the way around this thing just in the same way that light gets bent when it goes through a lens. So we call that gravitational lensing. And here's the kicker. This is the thing that's going to become really important when we talk about dark matter, is that how much this bends, how much bending we get right here, is dictated by the mass of the sun. So the mass in between us. So we can tell, right, how much stuff is in the middle, whatever is making this bend. It could be a galaxy, it can be a star, it can be something else, it could be dark matter. Whatever the mass of that is, dictates how much these light rays get bent as they go around that thing. And that's going to be key.